back to looking at our spring mass system that we started looking at yesterday, and what we had ended up with was a system that looks like this, a tridiagonal matrix here. And so it's going to end up that solving these systems is actually really easy, but what we'll do is we'll solve it on Matlab here in a minute, and then we'll see you know, if there's a better way that we can solve systems that look like this. Okay, so let's switch over to Matlab. All right, and now that we're in Matlab, you can see that large tridiagonal matrix. I put in here our displacement at the very beginning and our displacement at the very end of our 2-second interval, and then just generated the vector b, which, remember, is mostly zeros other than that first entry and last entry, and that's just because we happen to know the displacement at these 2 points in time. And then the next thing I have here is actually the solution. Okay, and maybe let's plot it real quick, just see what it looks like. So easy plot, function u, and we're only trying to solve this system from t equals 0 to 2. Okay. All right, and here it is. Okay. And so what we're going to do here in a moment is we are going to try and look at this over, or we're going to compare this graph with what we get from our numerical solution. Okay. All right, so to get that numerical solution, for one, again, we know the initial displacement and the final displacement. Okay. So I'm going to call the displacements, let me see if I've used, I haven't yet. Let's go ahead and use little u for our displacement. And let's say that first one, right, we have to index starting at 1. We can't index starting at 0, minus 0.5. And also the last one. So remember, on our number line, we started at u sub 0 and ended at u sub 8. Well, since we're starting at u sub 1, because of how we index in Matlab, then that means we're going to end at 9. Okay. So that takes care of the endpoints, but to get the middle ones, that's what this system here is for. This was supposed to find us u sub 1, u sub 2, u sub 3, u sub 4, u sub 5, up to u sub 7. Okay. But again, we've been pushed off 1 unit here. So instead of our matrix there helping us find u1 through u7, it's going to help us find u2 through u8. Okay. u2 through u8. And so what I'm going to do is I'm going to note in here that is what we really want to do is fill in the entries 2 through 8 with what we're going to get from this backslash command. So I'm going to just do a backslash b. Okay. Yep, and we called our matrix A, so good. Okay. So this should generate all of those displacements. Now, the next thing that we need to go along with this is we need to set up the x values, right? We don't have the x values to go along with this, or t values. Okay. So in order to do that, let's just use linspace. Okay. I'll just use x. X equals linspace. We want to go from 0 to 2. Okay. And remember, if we were to sketch out that number line and write in 0, 0.25, 0.5, 0.75, all the way up to 2, that would give us 9 different tick marks. Okay, so we want 9 points starting at 0, ending at 2, and equally spaced. Okay. This should give us the desired spacing. And then the last thing we need to do is just plot. So plot and x comma u. And one thing I'd like to do is note that this actually does look kind of similar to what we had before. Of course, we're only making measurements every 0.25 seconds, or approximations every 0.25 seconds. So this isn't going to be perfect, but let's put this up against the actual solution. I just need to put a hold on here. All right, there we go. So again, not bad for doing, an approximation every quarter of a second. Now, the issue would be, right, if we wanted to maybe do this for every 0.1 second, the math itself that we did in OneNote wouldn't change much, okay? But the matrix that we would end up with would be a lot larger than this. Okay? And so is what I'm trying to say is we would like to find a more efficient way to solve a system like this. We don't want to have to type in all this, especially when most of this is just zeros. Okay? So what we're going to do is we're going to figure out right now what we can do to solve systems like this a little bit easier. Okay? And we'll create a function that'll help us solve these types of problems easier. So let's go ahead and switch to OneNote. All right, here is a general tridiagonal system. I suppose it's not a system unless I include the other side of this. Let me augment this real quick. Here we go. And so on the augmented side, we'll use R's. There we go. All right, I do want you to note how we're notating this. The diagonal row we're calling F. The one above the diagonal we're calling G. And the one below F we're calling E. And then this vector that we usually call B, this will be our R vector. So when we do create our tridiagonal function, the inputs will just be the vector that is this upper diagonal, a vector that's the middle diagonal, a vector that's the lower, and then a vector that is this right here. Okay. So next, let's look at an actual example. So here I've written it using kind of on the side here in green, the same notation that we were using up above, but here in the red is the actual example itself that we'll be doing. And it is what our first goal is to perform forward elimination. Okay. So in other words, my goal right now is to get all zeros below this 3 here. Okay. And notice I only really have actually one thing to get rid of, and that's the 2. The other 2 are already zeros because this is a tridiagonal system. Okay. Oh, I went back a little bit too far. That's okay. Here we go. So what I want you to see is after our first set of row operations, or actually our first row operation, which is row 2 minus 2/3 row 1. That's how we're going to recompute our row 2. Okay. But I want you to see how many things have actually changed going from here to here. Okay. Well, if we look, the top row looks the same. We got a 0 here, okay. But I want us to look for changes that are anything other than 0, because what's going to happen is row, or I should say diagonal E, is going to become zeros after we perform all our forward elimination. So there's really nothing to keep track of in terms of what's going to change there. Okay. And you'll notice that all these zeros will stay 0. Okay. But let's see what things other than zeros changed. okay? Or what things, okay? So if we look, we see this minus 1/3 here, and we see an 11/3 here. Okay? And notice that the rest of the values in this row didn't change other than the one that became 0, but the one after minus 1/3, it didn't change because it had a 0 above it. Okay? And same goes for the fourth entry in this row. It didn't change because it had a 0 above it. Okay? So only two things changed. And that would be F2 and R2. And those two calculations could have been thought of a little bit differently. We could have thought instead to get F2, our new F2, that we were just going to subtract E2 over F1 times G1. Okay. So the E2 over F1, that's just, let me actually write that in there. Let me remind you where E2 and F1 come from. So again, the whole goal in going from this first matrix to the second one was to eliminate the 2 right here. So in order to eliminate that 2, we had to divide row 1 by F1. That's where this F1 comes from down here. Okay. And then we needed to multiply it by the spot here in E2. Okay. And so that's where the E2 came from on top of here. Okay. And then this right here is just, again, performing the subtraction that was going to result in changing this to a minus 1/3. Okay? Because here we're working with F2 and G1, G1 being right here. So is what I'm really trying to get at though here is just two things changed, and we could have kind of simplified this process by just thinking about these two lines that I've written right here, because we know everything else is going to stay the same. Okay. Let's see what happens going from row operation 1 to row operation 2, or matrix 1 to matrix 3 here. What all has changed? Okay. Well, what has changed has been this number here and this one here, and nothing else. Okay. And so again, this could just be represented by these two little formulas. And I want you to check that by hand that this is exactly what's happening. Okay. And if we do another row operation, we'll see that still only two things change. Okay. And it was these two this time. Okay. So it's always been something that is in diagonal R and, diagonal F, the main diagonal, and something over here on the other side, okay, the R column. Okay. Let's go up and look at that. Yeah, it's always the diagonal. Well, this first one, nothing changed. But after that, something along the main diagonal, and something in R, main diagonal, something in R, main diagonal, something in R. So rather than doing a bunch of calculations, we're just going to do these little side calculations. Okay? That's it. That's going to save us from doing some unnecessary calculations. Okay? And we don't care about, again, all those other numbers that are 0. Okay? So the next thing would be, well, how are we going to perform our back substitution? And the answer is very simply, if I wanted to, say, find x4 first, which is what I should do because that's what's available to us at the moment, okay, I would just need to divide this number here, which is R4, by F4. And then we'd be solved for x4. Okay. And then if we want to find the next one, say x3, well, we have R3 here minus what's here. Okay, and so what's here where I just highlighted would be what would be considered G3, okay? And the variable associated with G3 is X4, okay? And so that's what's going on here. Okay? And then finally, once we've subtracted that over, we would then divide by what's right here, which is F3. Okay? And then if we went down to the next one, it would look very similar because, again, there's so many zeros already in this matrix. If we move on to this next one, we'd take what's here, okay, which is R2, and we would subtract the variable times this spot. So the variable here would be X3, but in terms of the notation we've been using, this would be G2. Okay. So we have R2 minus X3G2, and then we would just want to divide by this number here, F2. Okay. And again, it might help to actually try to do this by hand yourself here. And we'll keep doing this until we get down to X1. Everything looks the same other than X4. Okay? And by the same, I mean X3, X2, X1 seem to follow kind of this same little pattern. Okay? So let's go and try and code this into Matlab. All right, we are back in Matlab here. And I want you to first kind of note that anytime we're solving any matrix type problems, it's really important to know what the dimensions of that matrix are. Okay? And we won't actually be inputting the matrix itself. Remember, we're just going to put in the lower diagonal, the main diagonal, the upper diagonal, and then the other side of the system of equations. So the question is, well, how do we figure out what the dimensions of the matrix A would be? Like in our previous example, what would the dimensions of that be? And you could actually get it from two places here. So if, say, we were working with A being a 4x4 matrix, okay, then that would mean that R would have 4 entries in it. And also the main diagonal should also have 4 entries in it. But remember, the lower diagonal and upper diagonal, they're going to have actually 3 entries, 1 less entry. Okay. And we can take a peek at that real quick. Let's go up here. So if we look here, you can see the main diagonal has 4 elements, and the lower has 3, and the upper has 3. Okay. So if we're trying to get the dimension of the matrix A, is what we could do is we could just say, hey, let's take the length of F. And we're going to need that to set up our forward elimination here, because we're going to want to go for K equals, and let's go and see what we would need for K. All right. So if we go into OneNote here, notice that we started eliminating things, and maybe I'll get rid of one of these highlights here so that we don't mix it up. There we go. I think this was a 3. Okay. All right. Or actually, that should be that's not what I wanted to replace. This right here. Okay. So the question is, how many times are we, performing row operations? And so this was a 4x4. At least the matrix A was a 4x4. And what you can see is we had one row operation to get rid of something in row 2, which was actually a 2. Our next row operation was to get rid of something in row 3. Okay. And our last row operation was to get rid of something in R4. So we're making eliminations in all the rows except for the first one. So from 2 to 4. Okay. Let's go ahead and put that in our code here. from 2 to 4. Okay. And for us, right, 4 is n. All right, and then the next thing is we want the factor. Okay. Factor. Okay. And let's go peek at that as well. Here's our one note. So to get the factor, right, you want to take the element below the pivot and divide that by the pivot. Okay. And you can kind of see that that's what we've done here, is we took the thing that was below the pivot, and then we divided it by the pivot, right? Because this would be E2, and this would be F1. Okay. And so that's what's going to happen every time, because we're trying to eliminate what's below the pivot. That's the whole goal here. Okay. So let's go ahead and write that in, write in how we get our factor. So we get our factor by, again, taking what's below the pivot and dividing it by the pivot. Okay. And so we're going to need to kind of justify what's going on here. So you might know, why are we starting with k minus 1? Okay. Well, we want to divide by something that came in the previous row, right? If I were to go back in here, you'd see that, right, F1 came from the row above E2. And that's in part why we are calling E2 is it comes from row 2, F1 comes from row 1. Okay. So that's why the indexing is one different here. Okay. And also, probably slightly confusing, you might be asking, why aren't we using E of 2? Okay. E of 2. And the answer is we actually are using E of 2, right? We're starting at 2 here. But this should cause a little bit of confusion, because we probably all thought, right, E should have less elements than F. So that would mess with our indexing a little bit. But is what we're going to do is, let me go over here, is we are going to force E, F, and G to have the same number of elements. And this is how we'll do it. We'll let F of course contain everything from F1 to F4, and say E, we'll make it look like 0, and then E2 up to E4. Okay. And for G, it'll just be the opposite. It'll start at G1, and it will go to G3, and then we'll have a 0 at the end. That way all these vectors are the same length. Okay. All right, so now that we have our factor built in there, the next thing is we need to compute, and let me go back. We want to compute these things that I've kept highlighting next to the matrices, these little calculations. And remember the E2 over F1, that's just already taken care of in terms of our factor. So what we're going to write will look a little more simple than this. Okay, so after factor we have, well, let's compute the F's. Okay. And so note, again, this is going to start with the second F. The first F's not going to change. Okay, and the question is, in what way are we going to change F of k? Well, we're going to take F of k, and then we're going to subtract the factor times remember, the thing above it is G. The thing above, let me maybe move over here so you can see it. Okay. Right? The thing that's going to come from the previous row when we're thinking about, say, F2 is going to be G1. Okay. Right? If we were, again, looking at F2, maybe I should highlight it. If we were looking at F2, the thing above it is G1. Okay. So this is going to be times G of K minus 1. And then we want to do the same thing for R. So you can basically copy and paste this. So it should be R of K is equal to R of K minus the factor times the previous value of R. Because that's what's going to be above R of K would be R of K minus 1. Okay, so there's our for loop. Let's go ahead and end it. And now we want to perform our back substitution. And so remember, the first one that we got was actually x sub 4, or in our general case here, x of n. And that was found by just taking the last r value and dividing it by the last f value. And then next we'll want a little for loop that'll perform the rest of the back substitution. So for k, and let me make a little bit more space, for k is equal to, and we're going to start at n minus 1, and we want to go by minus ones, and we're going to end at 1 because we need to get everything from x sub n down to x sub 1. Okay. And then x of, okay. And let's go see what those little formulas look like. Right here. So all these purple ones other than the first one, we've already taken care of the first one. It looks like to get x3, you do r3 minus x4 times g3 over f3. And notice these all follow that similar pattern. Okay. Okay. So if you're finding, let's start off with maybe the easy part. Let's start off with all the things that the indexes match. So notice, if you're doing x2, it's r2, g2, f2. And if it's x3, it's r3, g3, f3. Let's maybe put those in there. So, right, we had an r of k minus x of something. We'll leave that out for now. Oh, and I'm missing a parenthesis there. There we go. So we have r of k minus x of something times g and it should be g of k, right? We said that that index was going to match. And so this takes care of the numerator, and now we'd like to divide this all by f of k. So the question is just what goes here? Let's go see how that compares in our OneNote. So the x always seems to be an index higher. Okay. But do remember we are, actually let's stick with that. Let's keep it simple. Yeah, this is one higher every time, right? Okay. So let's go back and put that in here. So this should be x of k plus 1. All right, and let's go ahead and end this and hit save. And we're going to go test this out on our system we were looking at. So we have a lot going on in here. I think I'm going to get rid of some of this stuff. Let's get rid of maybe we'll comment it out. Let's comment out all the graphing stuff here. I'm going to comment this out as well. And let's see, so far we still have our matrix A up here. We have the initial U, the final U, the vector B, and then we were filling our matrix U. This is just our solution if we were to hit run. Okay. So if we were to hit run, we could see our solution by jumping in here to this vector U. Let's see how that compares if we use our new function. So try diag, and we need to input some vectors here. So if we were to look at our vector G, okay, let's start off with G. Let's type that in. G equals, and let's just go ahead and type these in. Okay, so we should have what? 1, 2, 3, 4, 5, 6 13s, and then a 0. So 7 entries in G. Again, 1, 2, 3, 4, 5, 6, and then the 0. Okay. And then we have F, which F, since it's not going to have any zeros in it, I'm just going to use the ones command. So ones, and is what I'd like to do is create a vector of the same dimensions here. And the dimensions of this would be 1 by 7. Okay. And I just want to multiply all these 1s by 2 to get my diagonal. And then the last one is E, the lower diagonal, which we know starts off with a 0 and then should be a bunch of 3s. Okay. 6 3s to be specific. 1, 2. Okay. There we go. Right, and we already have the vector B in here, so we don't need anything extra there. And let's just go look at the order that Tridiag wanted E, F, G, R. Okay. So E, F, G, and R is B. Okay. And so we called the first one U. Let's maybe call this one U sub T for Tridiag. And you know what? Let me make sure that it actually outputs our other one as well so we can compare these results. But I had A being displayed and I don't want to see that anymore. Okay. Uh-oh, these are looking different, aren't they? And this just isn't giving us the same result because we've found all the inner points, but we did not write in what those initial and final ones would look like. So we could do something similar here. Could change this to U sub T of 1 and U sub T of 9. And this could be U sub T of, again, 2 to 8. Okay, and that should give us the same results here. Okay, there we go. Looks good.